In this flip, we will discuss metallic bonding and band theory. What makes metals so unique? Unlike non-metals, where electrons sharing is almost always within discrete molecular units, metal atoms share their outer valence electrons with all nearest neighboring atoms. It is the free movement of electrons throughout the metal structure that can be used to explain the high electrical and thermal conductivity of metals together with their high reflectivity. The lack of directional bonding can be used to account for the high malleability and ductility of most metals, since metal atoms can readily slide over one another to form new metallic bonds. Whereas simple covalent molecules generally have low melting points and ionic compounds have high melting points, metals have melting points ranging from -39 Celsius of mercury to 3400 Celsius for tungsten. Boiling point of metals correlates most closely with the strength of the metallic bond. For example, mercury has a boiling point at 357 Celsius and tungsten at 5660 Celsius. In the gas phase, some metallic elements like lithium exist as pairs, lithium-2, or like beryllium, as individual atoms, and hence lose their metallic properties. Metals in the gas phase do not even look metallic. There are two models that explain bonding in metals. The simplest metallic bonding model is the electron-C model. In this model, the valence electrons are free to move through the bulk metal structure, hence the term, and even leave the metal, thereby producing positive ions. It is valence electrons then that convey electric current, and it is the motion of the valence electrons that transfers heat through a metal. However, this model is more qualitative than quantitative. Second is molecular orbital theory that provides a more comprehensive model of metallic bonding. This extension of molecular orbital theory is sometimes called band theory. Let's illustrate band theory by looking at the orbitals of lithium. Previously, we saw that two lithium atoms combine in the gas phase to form the dilithium molecule. The molecular orbital diagram showing the mixing of two 2s atomic orbitals is on your left side of the slide. In this example, both sets of the atomic orbitals are shown on the left. Now, suppose that the atomic orbitals of 4 lithium atoms are mixed. Again, there must be the same number of sigma 2s molecular orbitals as 2s atomic orbitals, half of which are bonding and the other half anti-bonding. To avoid violating the quantum rules, the energies of the orbitals cannot be degenerate or the same energy. That is, one sigma 2s cannot have exactly the same energy as the other sigma 2s orbital. The figure in the middle shows the resulting orbital arrangement. In a large metal crystal, the orbitals of n atoms, where n is some enormous number, are mixed. These orbitals interact throughout the 3D of the metal crystal, yet the same principles of bonding apply. With such a large number of energy levels, the spacing of this level becomes so close that they essentially constitute to a continuum. This continuum is referred to as a band. For lithium, the band derived from the 2s atomic orbitals will be half filled, that is, the sigma 2s part of the band will be filled and the sigma star 2s part will be empty, as you can see from the figure on your right. We can use band theory to explain why some substances are electrical conductors, some are not, and some are semiconductors. In the metals, bands overlap and allow a free movement of the electrons. In nonmetals, bands are widely separated, so no electron movement can occur, therefore we call them insulators. In a few elements, typically metalloids or semimetals, the bands are close enough to allow only a small amount of electron excitation in the upper unoccupied bands. We call them semiconductors. To the right of the metals in the periodic table, there is a staircase of elements, the metalloids, that tend to have the physical properties of metals and the chemical properties of nonmetals. The metalloids are not as good as conducting electricity of metals, but they are better at it than nonmetals. In metalloids, conduction and valence bands don't overlap, but instead are separated by an energy gap. In silicon, the most abundant metalloid, band theory predicts an energy gap. Generally, only a few valence band electrons in silica have sufficient energy to move to the conduction band, which limits silicon's ability to conduct electricity and makes it as a semiconductor. However, we can enhance the conductivity of solid silicon or of any other elemental metalloid by replacing some of the silicon atoms with atoms of an element of similar atomic radii, but with a different number of valence electrons. The replacement process is called doping, and the added element is called dopant. Suppose the dopant is a group 15 element, such as phosphorus. Each phosphor atom has one more valence electron than the atom of the silicon it replaces. The energy of these additional electrons is different from the energy of the silicon electrons. They populate a narrow band labeled the p donor. P level. The small energy difference means that the donor electrons can easily reach the silicon conduction band, resulting in an enhanced conductivity. Phosphorus-doped silicon is an example of an N-type semiconductor, so called because the dopant donates negative charges electrons to the structure of the host element. The conductivity can be enhanced by replacing some silicon atoms with atoms of a group 13 element, such as gallium. Gallium atoms have one fewer valence electrons than silicon, so substituting gallium in the silicon structure means fewer valence electrons in the solid. The result is the creation of a narrow gallium acceptor level. Silicon valence electrons can move from valence band into the acceptor level, leaving behind positively charged quote-unquote holes represented by the positive symbols in the figure on the right. The presence of these positive holes and the migration of the electrons between them, filling one hole and creating another, enhances conductivity and makes silicon doped with gallium a p-type semiconductor. The semiconductor used in solid-state electronics are combinations of n-type and p-type.